Okay, crew, we are here with our 4-2 notes. This is the big idea of our Unit 4. So in these notes, we're going to talk about how to transform. Remember, transform means change, expressions, and how to prove an identity to show that it's true using our trigonometric properties. Now let's remember we've got 3 sets of properties that we know so far. We know our reciprocal properties or identities. We know our quotient identities. And we know our Pythagorean identities. And we're going to use those to change one expression to its equivalent, right, that looks different but means the same thing. So we're going to start with a graphical example. If you'll pull out your calculator, please. Pause and grab it if you need to. And in y1, I want you to graph the cosine squared of x minus the sine squared of x. In y2, graph 1 minus 2 times sine squared of x. Graph y1 as a thin line, graph y2 as a thick line, and I want you to see what happens. So I've got that here, and I'm going to pull in the document camera. I can do that. And let's look at what happens. So take out some of this here. So what I've entered in my calculator is I have y equals the cosine of x. Notice that I've closed the parentheses on my x, and then I have squared it. If I had squared the x before I closed the parentheses, I would be squaring my input before it goes inside of the cosine. But squaring after I close my parentheses on the input squares the entire function, the cosine. So I have the cosine of x, which is squared, that's the same thing as the cosine squared of x, minus the sine of x, again, which is squared. That's my first function. And I have the style of that line as thin. Then I've gone into y2, and I have 1 minus 2 times the sine of x squared, and I have the style of that as thick. So my mode is in radians right now. So if I go to my window, I have set my window from 0 to 2 pi, right? 2 pi, the same thing as our 6.28. I've set my y scale as pi over 4. And I went my y minimum -2, max of 2 on a scale of 1. So when I graph, right, this is what you should have seen. I would love to regraph that. Well, what you should have seen is, right, this sinusoid looking graph with 1 minus 2 times sine squared graphing right over the top of it. Right, so what the intention is for that to illustrate that even though those expressions look different, that they really give us exactly the same values. That confirms that they're equal. So here we go. Our job is to start with one expression and transform it into another. So I'm going to transform the sine of cotangent x into the cosine of x. So to do that, I'm going to start with my first expression, the sine of x times the cotangent of x. Okay. And I'm going to rewrite that with things that are equal. So I want to end up with only the cosine. I don't have a way of changing sine of x into anything that has a cosine, so I'm going to leave that alone. Now with the cotangent, right, we've got both reciprocal and quotient identities for cotangent. My quotient identity will give me a cosine for my cotangent. So according to my quotient identity, cotangent of x is the same thing as the cosine of x over the sine of x. Nice thing happens here. My sine of x will divide out, which leaves me nothing but my cosine of x. I started with sine of x, cotangent of x. I used my identities in my algebra to end up with the cosine of x. I have transformed the sine times the cotangent into the cosine of x. Let's look at another example. Here I want to transform the cosine squared of x minus sine squared of x into 1 minus 2 sine squared of x. We saw when we graphed those two functions that they truly are equivalent, or at least they appear to be. So let's start. We're going to take cosine squared of x minus sine squared of x. And I want to make substitutions, replacements for one or both of those functions to end up with 1 minus 2 sine squared. Well, I don't want a cosine squared, but I do want a sine squared. I actually want two of them. So I'm going to leave this sine squared alone. I'm going to not change that one. But I'm going to come in here to the cosine squared of x. And since it's squared, I'm going to think about my Pythagorean identities. And one of those Pythagorean identities says that the cosine squared is the same thing as 1 minus the sine squared of x. So I replace cosine squared with its equivalent, and now I just do my algebra. 1 minus a sine squared minus another sine squared is 1 minus 2 times sine squared of x. And I have transformed. I went from cosine squared of x minus sine squared of x, right, into 1 minus 2 sine squared of x. That's where I ended up. Okay? So that's the idea. Let's go and look at something else. So here's kind of another idea we want to work on. An identity is an equation, right? So it's an equation which states that two expressions are equivalent. They measure the same quantity. To prove an identity, we work with one side of the equation only. Do not work with both sides, right? And we transform it, we change that one side until it is identical to the other side. Don't change both sides. Okay? You pick one side, you work with it. If you get to a point where that's not working, then you start over and you can work with the other side, but you can't work with both sides in the same proof. So here's an example of how that can work. I want to prove that 1 plus cosine of x times 1 minus cosine of x equals sine squared of x. I want to prove that that's an identity. So I'm going to work with one side. In general, it's easier if we work with the more complicated side and simplify it than it is to work with the simple side and try to complicate it. Right? We all know that we're very good at complicating stuff. Unfortunately, we each tend to complicate things in different ways. So we're going to start with the more complicated side, which in this case is our left side, and we're going to simplify it. So we're going to ask ourselves, what is it I can do with 1 plus cosine x times 1 minus cosine x? Okay, trying to figure out what to do takes some experience. It takes some trial and error. It often takes some frustration, some failure to get to the point where you start sensing, seeing what to do, what your options are, what might work, what might not work, and to develop the confidence just to jump in and try, and if it fails, to try over. Right. So one of the things we do is we think about just doing the math that's there. This left side tells me to multiply those two quantities together. They're binomials, two terms in each parenthesis, so we're going to FOIL them. So we do the first, 1 times 1 is 1. Then we do the outers. 1 times a negative cosine is negative cosine of x. Then we do the inners. Positive cosine times 1 is a positive cosine of x. Then we do the last. Positive cosine times negative cosine is negative cosine squared of x. That's my left side. I'm going to keep this as an equation, and I'm not going to change the right side. It's going to stay sine squared of x all the way as I work down in this problem. Now I've got another bit of math I can do. I have two opposites that I'm adding. So opposites add out, that becomes 0, and what I'm left with is 1 minus the cosine squared of x. That's supposed to equal the sine squared of x. Okay, now hopefully you're looking at 1 minus cosine squared and you're saying, hey, that's a Pythagorean identity. That does equal sine squared of x. But you're not done until the left and the right side are identical. So using that very thinking, we replace 1 minus cosine squared x with its Pythagorean identity, which is sine squared of x, right? That's supposed to equal sine squared of x. The two sides are identical, and we have proven our identity. Let's look at another one. This time, we're going to prove that the cotangent of A plus the tangent of A equals the cosecant of A times the secant of A. So, right, which side is more complicated? Well, both cotangent, tangent, cosecant, and secant can be rewritten as fractions. And to add two fractions is more complicated than to multiply. So we're going to start again with this left side. And this may not be intuitive, but one of the things we often do, especially with expressions that are complicated and we don't see a direct connection between one side and the other, is to change all our trig functions so that they are in terms of cosine and sine. So I'm going to start with this cotangent of x, and I'm going to change it to its quotient identity, which is the cosine of A over the sine of A. So changing cotangent using cosine and sine, I have a fraction, cosine over sine. Now to that I'm going to add what the tangent of A equals. Its quotient identity is the sine of A excuse me, over the cosine of A. And that's supposed to equal the cosecant of A times the secant of A. I'm going to rewrite that at every step, but that right side is not going to change. All right, now I have two fractions. What do I need to do if I'm going to try to add two fractions? Well, I need a common denominator. Very often a common denominator is the product of the different denominators we have. So I have a sine of A, I have a cosine of A. My common denominator is going to be the sine of A times the cosine of A. Now, for me to change the first fraction so its denominator is sine times cosine, I'm going to have to multiply it by a cosine. And what I multiply the bottom by, I have to multiply the top by, right? That's okay because I am multiplying by what is essentially 1. So when I multiply these two fractions together, right, I multiply the tops and I multiply the bottoms. The tops multiply give me a cosine squared of A. Now to add the second fraction, I'm going to have to multiply the second fraction by a sine of A over a sine of A. Right? That gives me cosine times sine, which is sine times cosine. I'm multiplying by 1, and what I get on top, right, when I multiply those numerators, is I get my sine times my sine, which is my sine squared of A. So again, that's supposed to equal the cosecant of A times the secant of A. Now it may not look to you like we've gotten into a simpler situation, but think about what cosine squared of A plus sine squared of A is. That's our Pythagorean identity. That equals 1. So we now have 1 over the sine of A times the cosine of A. Does that equal the cosecant of A times the secant of A? Well, there's a property of multiplication that says if I'm multiplying two fractions together, so I have 1 over A times 1 over B, that we multiply the tops, we would get 1 in this case, and we multiply the bottoms, we get 1 over AB. Well, if I can go from multiplying two fractions to getting one fraction where the denominators are multiplied together, then I can go back the other way, which means that when we have a fraction, right, a number on top over two things that are multiplied, we can split that into a product of two fractions. Applying that idea here, I can take 1 over sine of A times cosine of A and split that into 1 over the sine of A times 1 over the cosine of A. Okay. If I multiply these two fractions together, won't I get the sine of A times cosine of A? Yes. Now, those are each reciprocal identities. 1 over the sine of A is the same thing as the cosecant of A, and 1 over cosine of A is the same thing as the secant of A. My left side now looks exactly like my right side, and I have proven that identity. Okay. So what we're doing is not easy, but it's not terribly hard if you know your identities. If you don't know those reciprocal, quotient, and Pythagorean identities, then your toolbox is empty. And when you look in your toolbox for something to do, you won't find any tools that are going to be helpful to you. But if you know those identities and they're right there on top, you're ready to use them, then you're going to start seeing what to do and be willing to try new things. All right, let's look at another one. So this one involves something creative that you probably wouldn't think about if you didn't see it, but I'm going to show you. So we're going to start with one side, and as we look at this, I don't know that the left and right side are very different in their difficulty, but I'm going to start with the left side. We just usually do, but where they're equal in difficulty. So I have 1 over cosine of b over the sine of b, and that's supposed to equal the sine of b over 1 plus the cosine of b. If we think about the top here, 1 minus cosine of b, if that were a 1 minus cosine squared of b, I'd have a Pythagorean identity which would allow me to go from cosine to sine. But it's not 1 minus cosine squared, it's only 1 minus cosine. But if I multiply that difference by its conjugate, so by 1 plus that cosine of b, and if what I multiply the top by, I have to multiply the bottom by. So I multiply the bottom by 1 minus cosine of b. Then watch what happens, right? So this is still going to be an equal sign. When I multiply these tops together, I'm going to FOIL those together, and I get 1, right, minus cosine of b plus cosine of b minus cosine squared of b, where those two middle terms will subtract out. Now on the bottom of my fraction, just because I've done this before, I know what's going to happen. You haven't done it yet, but you're going to see what's going to happen. I'm going to leave the bottom as multiplied. This has the 1 plus cosine, which I want. I'd love to get rid of the sine, so I'm not going to multiply these together. I'm just going to write them as being multiplied together and watch what happens. So I now have, right, so this is supposed to be sine of b over 1 plus cosine of b. And I now have on top 1 minus cosine squared of b over my 1 plus cosine of b times sine of b. Well, what is that 1 minus cosine squared of b? Isn't that the Pythagorean identity I was wishing I had? I take that and I replace that with a sine squared of b over my 1 plus cosine of b times my sine of b. Right. I want that to equal the sine of b over 1 plus the cosine of b. And something nice happens. This sine of b will divide out by one of these two. Remember, sine squared means I have a sine of b times another sine of b. Where does that leave me? That leaves me exactly where I want to be. I've got 1 sine of b on top. I have 1 plus the cosine of b on the bottom, which is exactly identical to what I have on the right side. And I have proven that identity. So that idea of having a difference or a sum of two single degree trig functions to get a Pythagorean idea by multiplying by the conjugate can be really helpful to remember. So in general, this is what we want to do. To prove an identity, we want to pick which side of the expression to work with. Usually it's going to be the more complicated side. We want to look for algebraic things to do. Some of those, which we saw in an example today, was to add fractions. Right? And remember, to do that, you want to get a lowest common denominator. To factor, right? And we might factor out a GCF, right? Or we might factor by foiling backwards. I call that lie-off, right? Or other ways of factoring. And we might actually multiply or add or just do whatever math is called for in the expression. Another thing we often do is multiply by a clever form of 1, right? That might be the conjugate of the numerator or denominator. We just saw how that worked well. And we might multiply by a clever form of 1 in order to get the desired expression in the numerator or denominator. We often will use trigonometric properties. That's why we're learning them. If we have squares, you want to think about your Pythagorean identities. If we need to cancel something, right, divide something out, you might think about either a quotient property or a reciprocal property, because those both involve fractions. Right? Another thing that works well, oftentimes it's not always the most efficient way, but if you can't think of anything else to do, at least try to change everything in terms of sine and cosine, like changing tangent to sine over cosine. And finally, keep referring to the goal. Right? What is that other side that you're trying to get identical to you? Are you getting to where you want to go? It's a process. It takes trial and error. It takes learning. It's kind of like learning to drive. You just have to start. You got to try, play it safe, right? As you get better, more confident, you can handle more difficult situations. So you guys are a super, super bright group. I know that you can do this. Hang in there. Be positive. Be courageous. And be confident. Love you guys. And look forward to seeing you tomorrow or on our next class day.